start. And thanks to Katya, it was really nice to have a Mozambique presentation just before mine, because we'll be staying in Mozambique. And I can say I've kept the co-authors on here, but most of them are here in the room. Florence and Asper, who's joined us from Dime, and Valerie from IFPRI. And one who's not here is Tobias Siegfried, who's an engineer. So before I get back to Mozambique, just giving the broader context, I think most people in this room are probably familiar with this perplexing head-scratching problem of going out to rural areas and seeing broken down irrigation systems that seem to have failed for an easy, solvable reason. Sometimes it's a broken pump that the whole irrigation scheme has gone to waste because of one part, a low-cost part that needs to be fixed. Sometimes it's the experience of actually talking to the farmers and hearing from the tail enders at the bottom of the scheme. Oh, sorry. Close enough? Apologies. So sometimes it's the experience of going to the tail end of the scheme and hearing farmers there at the bottom of the scheme saying that they don't have enough access to the water, even though if you go to the top of the scheme, people report that they have plenty of water to spare. But most of these problems are rooted, as is well known, in common pool resource problems that lead to free rider externalities. So often this is individuals making decisions about how to use water or how to manage the scheme that don't account for external effects. So examples are farmers don't share water efficiently, even though in the socially optimal allocation, there would be enough for everyone to get water to meet their requirements. So often in developing countries, this is solved by pricing, where all of us have metered water that we pay for the water we use. But in some contexts, the infrastructure doesn't exist to have such a neat solution. So we're looking at the kind of nudges that are needed to get to more efficient solutions if you don't have that infrastructure. So we'll get to how we, apologies for the graph, but we'll get to how this data is produced in a second. But I just wanted to show the kind of collective action problem we're talking about here. We just look at this graph, which shows the number of people who are who have different levels of water, and being below 0 means you're not getting enough water to actually water the crops that you're growing. So we see that there are some people to the left of that line who are not even getting enough water for to meet the recommendations for their crops, and some people are way above the line. And the really striking thing about this is it's not the case that everyone is constrained by water, and so everyone is just using as much as you can. The people who are using the most water are actually getting a lower return from water than people to the left of them. So the striking problem here is if you just took the water from the most egregious water users, who may even be overwatering and waterlogging the crops, you could get rid of the scarcity in the scheme. So that's the problem I want to have in mind as we get to how we collect this data and the contributions we're making with this data. So the general overall question is when we have a problem like this of inefficient allocations, can we come up with interventions that are low cost and implementable in a constrained environment that can solve these collective action problems? And we think of there being two parts to this. So first of all, how do you set up the monitoring system that will reveal the sorts of rules of what we call rules of thumb that lead to the suboptimal cooperative behavior? And if you can identify these, if you can get the kind of data you need to find out where the glitches are happening, what is the kind of feedback or information you need to provide in order to sort of reboot people back to more efficient allocations? So the two sub-questions to that are, first of all, is general sort of extension information enough? Or is it really the case that you need to have measured this thing carefully in order to give people individualized feedback on their usage, in order to get them to understand how to act on the generalized recommendations that are typical in an extension environment? So the way we think of this being a contribution to the overall literature instead of just how to run irrigation schemes in Mozambique, first of all, we're demonstrating the feasibility of a high-frequency monitoring system for irrigation that uses local involvement of citizens, engaged farmers, rather than sensors. We're not the first people to do this, but it's an additional sort of demonstration of the feasibility of these things. And second, we use this high-frequency 1 year a time series of data in order to demonstrate the kinds of rules of thumb that farmers are using that lead to inefficiency. I'll explain more what we mean by that in a second. And then after we've had the opportunity to see farmers' behavior and identify the sticking points that we think are key to the inefficient allocations, we implement a feedback experiment to isolate which parts of the information provision is key to acting on and solving the inefficiency we see. And that part of the paper is similar to the literature on using metered information and individualized feedback in order to generate pressure to conserve. So the most similar sort of papers there are the kinds of the O-Power experiments in California on increasing the salience of information from metering on resource use in order to generate more sustainable use. So thankfully, I don't need to present too much about what Mozambique is like, because we've got a nice view of that. But just briefly, the context we're talking about, so starting in May 2015, we started a measurement pilot in 3 irrigation schemes in central Mozambique. 2 of these are gravity surface, so canal irrigation, and one of them is a combination of canal gravity-fed systems and sprinkler pump systems. And there were a lot of people engaged in this work, so including the partners I just mentioned, who are co-authors on this paper, but also collaborators within Mozambique from Eduardo Mondlane University and the National Institute of Irrigation. So after all that set up and motivating, it's a big part of this paper is how to actually pull this off. Because one of the nice experiences about this paper is talking to everyone else who's tried to measure irrigation and all the things that go wrong trying this, because it's a very difficult thing to do. So the approach we took is we worked with some engineers from Hydro Solutions to set up a system and to go measure the schemes and calibrate. If you wanted to estimate volumes being delivered as close as possible to the plot scale, which points would you need to measure, and how would you measure depths and flows in order to estimate volume? Once they have that sort of technical calibration in place, they train local farmers who are part of the local water management infrastructure to collect those specific measurements every day. So they teach them, at this point on the canal, you need to collect the depth, and then move on to the sprinkler and collect in the length of time it takes to fill up this bucket. And then that data all gets collected. It's measured 3 times a day, every day throughout the year. It's collected by an extension worker who logs that into a book and then sends it to the central level. So we have the calibration done in advance in order to convert that stream of measurement into volumetric estimates that can be assigned to plots. So this is one way of looking at what that continuous stream of data looks like. So it's just to show the 2 main important features is really a continuous scale of irrigation. So we have this is weeks on the bottom, so this is running over a year, uninterrupted flows of how much water is flowing through the schemes, and it tracks the sort of reasonable kind of things that you expect. So blue lines are irrigation flows through the canals, and the orange line is rainfall, and you can see this reasonably tracks the kind of natural phenomenon in terms of rainfall spikes being represented in the data. But the most interesting use of this thing is being able to assign these volumetric measurements that we get 3 times a day, but can be aggregated to weeks or months, and assigning them to plots. So because we measure at many points throughout the scheme, we can estimate the volume of water being made available to each plot within the scheme. And then you can aggregate this over different timescales to see how water use is changing throughout the scheme. And you can see kind of expected patterns, like for example, blue represents having more than typical water available, red is less than typical water. And you see the kind of patterns you'd expect in terms of people on the upper end of the scheme having more control, and so therefore greater water availability, and also over time shifting from a relatively rainy, water plentiful season to the dry season, scarcity develops over time. So we see that we've captured a lot of the features we're looking for in terms of water availability and the amount of water that farmers are able to apply to their plots. So that's the water flow. Where this becomes really useful and interesting is looking at how farmers are actually using the water that's made available. So layered on top of this continuous stream 3 times a day, every day, collection of water, we do household interviews with an agriculture module. So we've now done 5 of these. One of them starting a few months after we started collecting the water. And from this, we're able to learn which crops farmers are planting on their plots during the months for which we have the water data, the months that they planted, harvested, and we're able to match water flows to production decisions. So what do we learn from all this about how farmers are or not using water efficiently? So the most striking, easy way to see this is the lines on the graph here are the water requirements for the 3 main crops that are most commonly planted by the farmers in the schemes. These are primarily horticultural farmers who plant cabbages and baby corn for commercial markets. And the feature of all of those crops is that they require far less water in the early stages, right after you're planting them, and the plant is very small, than they do later on, just before harvest. So particularly when the plant starts to flower is when it needs the most water. So if you were just meeting the requirements of your crops, what you would do is apply less water at the beginning and then ramp up water allocations as the crop develops and then maybe taper off a bit at the end. But the gray bars are the average water delivered to plots over time by farmers within the schemes. And what you see is the actual allocations don't track these requirements at all. So what it looks like farmers are doing from this way is they know what the maximum requirement is for the crop over its whole cycle. They ensure that that much water will be, or try to get as close to that much water being delivered as they can, and they keep it at that level consistently throughout the whole scheme. So that reveals a very intuitive way to try to improve allocations, which is deliver less water at the very beginning in order to make deliveries of water match requirements. That requires one additional thing, which is that not everyone is planting at the same time, because it's not helpful to say we're going to make less water available at the beginning if everyone is going to be needing water at the same time. Fortunately, it appears that that the planting allocations are staggered in such a way that farmers are already not overlapping growth stages, so it suggests that there would be additional water available. So how does this relate to individual farmers? So this is average allocations over time. You see this flat pattern. If we look at the distribution of allocations over time and separate it by growth stage, the consequence of that sort of allocation is what we see here. So lighter bars are earlier in the plant growth stages, and darker bars are as you're moving later. And what you see is because everyone is targeting this higher amount consistently, but requirements are changing over time, in the early growth stages, so the lightest bar, virtually everyone is using more water than is needed for their crops. And the consequence of that is by the time you get to the later stage, because some farmers are overusing in the early stage, there are a lot of people who are not managing to meet their recommended water delivery and are probably suffering loss of potential production as a result. So the question we posed for ourselves after seeing this data and after seeing this result is how do you move people from using less water in the light colored distribution so that there's more water available for those in the dark lines to move them to the right of that red vertical line and get them up to sufficiency. Sorry, this is the plot of the staggering. So you can see that over time, because people are not planting and harvesting all in the same month, it is actually possible. If you move people from the far right side, you would have people who are in the far left side of this in the later growth stages, because you see this relatively staggered pattern of planting and harvesting, cycling virtually continuously. So what is the experiment we decided to run? So after seeing this pattern, our hypothesis was that the crucial bit of feedback is related to the timing of water allocations to crops, and if you can improve that, you could solve a lot of inefficiency. So because we only have 3 schemes with 30 to 40 farmers per scheme, we only have 100 farmers, so we don't have a lot of power to give ourselves a huge variety of options in testing nuanced versions. So we went with the strongest push we could, which is everybody's going to get something. So this is a combination of an event study where everyone gets something, and then we layer on a randomized additional treatment to see the additional impact of individualized feedback. So the first big push is giving people the typical extension that's sort of not tethered to their individual use, but is just a reminder of what average water recommendations are needed, which is based on the plant's biology and not their own water allegations. The other 50% will get that information plus individualized feedback on how that recommendation compares to the water that they actually use. And we did this through match pairs randomization, where we created match pairs of the most egregious overusers and the highest underusers, and then randomly assigned one member of that pair to get the additional feedback. So in terms of timeline, the way we did this is we spent 1 year collecting a full time path of the measurement data plus the household agriculture modules. in order to identify this effect. So we did these first 4 rounds, staggered along seasons, and then at the point where we finally had a full year covering every season, we went in with this, this feedback tool and followed up with 1 more survey so we could see how the tool impacted household production. This is what the tools actually look like. So everybody gets at least the thing on the left, which is just for the most important crop that you grow on your plot, what is the recommended watering schedule? So just reminding people that, hey, your crops actually need a lot less water at the very beginning than they're going to need at the end. And the experiment is adding on individualized feedback. So the hypothesis is that maybe the failure of typical extension is that farmers are able to understand the recommendations, but because they're not able to easily monitor water flows, they don't know how to act on that information accurately. So we layered on providing them just the recommendation plus an estimate for in the same season last year, so as close as we can match to the same weeks that you were cultivating last year, how much water were you making available to your plot in the season in which you were at the growth stage in which these recommendations are given. So you can see, you get a comparison of the bar. The dark bar is what you used last year, and the light bar is the recommendation for the next year. So here's the overall picture of what happened. So the solid lines are the distribution of water being delivered to plots prior to the information experiment, and the dotted lines are what happened in the after effects. So we see farmers in both groups, both types of treatments, using far less water than they did before. So most of the action is happening from just delivering the information, with only sort of a minor difference between delivering the individualized feedback. So the consequences of that, looking at this from just an event study approach, so the blue bars are all the data we collected in the year prior to the feedback experiment, and the red bars are what people were doing afterwards. And this is average water delivered to plots across all of the schemes. What we see is immediately after provision of the feedback, water use drops. So it falls from 4 millimeters per day in January to below 5 millimeters per day in January to below 4 millimeters per day in the same month the following year. So obviously that confuses a time trend. It may just be that it rained less in that year and so less water was available, and this may be a reduction of water use that harmed farmers. But we can look at whether farmers actually had enough water available in 2 ways. So one is asking them, have you had any conflicts or disputes with your neighbors about the amount of water delivered? And what we see is for a couple of months, conflict tracks where it was before, but then 3 months after the feedback intervention, conflict entirely disappears. It's hard to see, but the actual relevant feature is that we would have data in January, February, and March, but there's actually no red bar there, because farmers went from 10% of farmers reporting conflict in those months last year to no conflict being reported after the information, the reminder had been given, even though farmers are using less water. So they're using less water, but reporting fewer disputes over the quantity of water. Another way to look at the same effect is to ask them, do you think that you had enough water delivered to your plot? And what we see there is, again, for a couple of months, it stays around the same level it was next year, but after some time to reallocate, despite the fact that they're using 20 to 30% less water than they did the previous year, reports of sufficiency jump all the way up to 100%. So reported insufficient water intake has disappeared after the feedback provision. So looking at this in terms of the graph that we used before and actually using the individualized feedback, the top graphs are what the water use relative to requirement looked like before the treatment. So again, the most salient thing is early growth stages, everybody's to the right of that bar. Late growth stages, lots of people are to the left. The bottom is after the treatment, so after we provided information. And what you see is there's virtually no one now to the left of the red bar. So in everyone has moved to having enough water. And where that comes from is before you had this misalignment of, in early growth stages, people using far too much water, to now they're lining up their water use close to requirements in both growth stages. So there's a compression around the actual requirements in both groups, and far fewer people using less water. So we're at the point now, we just got this data a couple weeks ago and have started to see these effects, but we're at the point of trying to disentangle these 2 treatments, because as you can see, a lot of the action comes from the pre-post, and the effects are more nuanced between how much the individualized information matters. One simple way to look at that is just the share of people who are falling below that red line of having insufficient water, and looking at the effect. So the post effect would be the event study design of the effective information overall. And then we can interact that with whether you are randomly assigned to get individualized information. And what we see so far in this rough cut of this approach is all the action seems to be coming from getting the information, getting the reminder. So the typical kind of easy, cheap to implement extension reminder of just go remind people how much water their crops need seems to be doing a lot of the work without actually needing to have this expensive monitoring for every single farmer who's receiving a recommendation. So I'm looking forward to discuss some suggestions, because this is a very preliminary approach to how to deal with that problem. There's a lot of additional ways to sort out those treatment effects, but that's really the next step for this. So first of all, we've shown some of the effects on water sufficiency, but what we really care about is yield. So since we have farmers' reports of their production, we want to see whether this information is actually improving or at least holding constant farmers' yields and profits while saving this water. Next, refining the measure of how information improves efficiency. So that sort of difference specification I just showed of the proportion insufficient is a very rough cut of disentangling the treatment effects. So we're looking at better ways of doing that, taking advantage of the fact that we really know in this long time series where the information treatment happened. So a better, more sophisticated event study design rather than the simple differences. We're also interested in knowing, we have a very clear prediction of how underusers and overusers at baseline should have reacted to this information. So heterogeneous effects by whether you are an overuser or an underuser is a clear next step. And then finally, we have information about your perceptions of your own water use and your perceptions of other people's water use. And we're interested in whether the individualized feedback helps people get a more accurate estimate of both their own use and others' use in helping them mediate conflicts with others. So we'll start leveraging some of that perceptions data. And then finally, this is still an active ongoing pilot with planned rounds of data collection. So we'd love to get feedback on, we have limited power, we have a limited number of observations, so we're not going to be able to do every treatment arm that we could think of, but we'd love feedback on what are the highest priority treatment arms, especially as the dry season comes. So this first experiment is a relatively water plentiful season, but the dry season is coming, so water scarcity is going to be much more vital. So interesting time to tackle that.
Thank you so much. I've really enjoyed reading the paper, and I really like the idea of measuring the volume of water going to the field, because in water use efficiency, the main challenge obviously is measurement. So you can't really optimize or talk about efficiency for something that you are able to measure. So that is, I think, a very interesting point. So having said that, I have a few questions or comments or suggestions in regard to the paper. So first of all, yes, there could be differences across different growth stages in water requirement by crops. But for me, I think the first starting point would have been differences in water requirements across crops. So are farmers, using the same amount of water for all the crops? Because it's easier for them to understand that tomatoes require more water than maize, for example. So that I initially missed that point. So probably that has to do with the sample issue. But I think it's important at least to highlight descriptively that if farmers are using actually the same amount of water, there is some kind of behavioral strategic thing going on, that if they don't use the water when they get it, they may not get it at the end. So I think that's the first point I have on this one. The second one is, since this is a pre and post identification, and the information intervention started in December 2016. And as you said in the introduction section, in 2016, Mozambique has a drought. So the assumption, this parallel trend assumption becomes, I'm not sure it holds. So my concern there is, are you seeing this reduction in water use because of the drought or because of the fact that you don't have the water, the difference between the two treatment arms also raises or reinforces my concern that people are just, there is not enough water in the canal. So that is the second point that I have there. Uh, and I know you have tried to use conflicts. There is no conflict, so there is no shortage of water, but we know there is shortage of water because the drought already happened. So I think I don't find that the theory of no conflicts issue very convincing for the drought. The other one is probably this one is, I'm sure you will revise it in the next stages. I like the idea of the measurement, but it's not described anywhere in the paper. So, uh, for someone who has tried previously and failed to actually measure, do a volumetric measure of this water, it's really important. If you can just summarize, this is how you have done it. I think it has better come out in the presentation, but not in the text. So there is a link to the website, but it doesn't describe anything. That's the other point that I have. Uh, the fourth point I have is from the experimental design, since everyone is monitored and provided feedback on what the requirements for the crop, we won't be able to know whether farmers are responding to being observed. You are observing them 3 times a day for the whole year. You should expect for farmers to change their behavior just by being monitored. And I think, is it the information or is it the monitoring? I would have liked that one. Unfortunately, the sample doesn't allow you to do that. But as a suggestion, you are giving the information only for the primary crop, right? So if you are giving them this information both on their actual use and on the crop requirements, you are giving them for their primary crop only. So you may be able to compare water use for the primary crop versus their secondary crop because you didn't give them anything for the secondary crop. So if the data allows it, I think that's something that you can try. The other concern I have is you have shown that farmers overuse water at the first two stages, growth stages. And my concern is that I might be wrong, but my concern is probably the first two stages coincide with the onset of the rainy season. So there is a lot of water at the beginning of the rainy season, so they are most likely to use at the beginning. Uh, so this is something easy to show probably from your data. For instance, you can show the water gap figures. I think the water gap distributions separately for the dry season versus the wet season because the rain is not going to have significant impact for the dry season. The other related question is, at least for the canal-based schemes, if the volume of water coming to their field is too much, do farmers have a mechanism to reduce the channel, to open the channel partially, or can they even close the channel if there is a lot of water at the beginning of the growing season, because without affecting their neighbors' water use? Uh, the other point that I have is, or probably the final point I have is uh, the very point collective action problem issue is still not addressed. If why would I save water in the first two stages if I'm not guaranteed that I'll get more water in the later two stages? If I expect other people to actually continue overusing, I might do as well. And if even if I assume other people will reduce their volume of water, I might assume that my effect is going to be significant, so I will still overuse. So you have already raised it at the future step on collective issue when you discuss about our future plans for comparing private incentives versus social pressure, but I think that needs to be developed. Overall, I really enjoyed the paper and happy to share the comments. Thank you.